Okay, so I think everything is on now. Okay, good morning, folks. So before we get started with the topic for today, I just want to make mention of some things I already posted in the announcement sections in Canvas. And that has to do with the final exam. I've decided, as I have announced, that I'll make it a take-home exercise, which will be published on the 3rd and due on the 7th, all right, of August. Now, as far as test number 3 is concerned, I've been really struggling with it this morning in terms of when I should make it available, because as you all know, we're coming down to the end of the term. So what I've decided to do, and I just decided it this morning just before I signed on, I'll make the test number 3 also a take-home exercise as well. I'm going to post it in Canvas. And let me see here, because I have to turn in the grades on the 10th. So I need to get some time, of course, to grade it. So let me see when I should make it due. Hold on, let me see. Let me see here. So the 10th is when everything is due. Okay, so what I'm going to do is I'm going to make the test number 3 be due on the 4th. All right. So just like how you would submit your assignments, you're going to submit the test in the same way as a PDF document. Make sure you write your name on each page and so on. All right. So I'm going to post that test later on today, and it's going to be due on the 4th at midnight. All right. And then the final exam, that will be due on the 7th, which would be Monday of next week. I'm also going to post that later on today as well. All right. So as I said before, I'm going to make an announcement or post that announcement in Canvas as well, so that you have that to remind you of those deadline dates. All right.
Professor?
Yes?
So since you're making it a at-home assignment, are you also going to do the keys with it, the past test keys?
I think I published, let me check here. I think I published the test keys for test number 3. Let me check. Whoops, no, not that one. I think I already published. Okay, pass this up. Yes, I have already published the past test key for test number 3. So you should be able to take a look at that. That should help you somewhat. All right. Okay, any other questions before we move on to today's topic? Any other questions concerning the announcements? All right, okay, so what I'm going to do now is commence with a discussion of assignment number 8, right? And as we said before, the last chapter is nuclear chemistry, and that's what assignment number 8 is all about. Okay, so let me scroll back up here and deal with the first question. It says, circle the missing particle. By the way, let me see, did I publish it? Let me see if I published assignment number 8.
You did.
Okay, good. All right, it's there, yeah. All right, so you guys can follow along. So the first question, it says, circle the missing particle in the following nuclear equations. Now remember, when you're given
your screen.
Oh, my bad. Let me take care of that now. Okay, so now you should be able to see it. So remember, whenever you're balancing nuclear equations, it's kind of different from balancing a normal chemical equation, because the whole idea behind balancing nuclear equations is that the total mass number must be conserved on both sides, and the same would be true for the atomic numbers, all right? So based on that idea, the question here is asking which of these options would be the one that would be the correct option that you'd put right here. And in order for us to do that, we'd have to add up all the mass numbers and all the atomic numbers. And since there's only one product, then that product should have the same sum of mass numbers and atomic numbers. And then based on the atomic number, you can determine the element itself. All right. Okay, so how would you tackle this one? Anybody? Well, let me ask you this. What's the sum total of the mass numbers?
$22.
I'm sorry?
22. 222. I'm sorry.
Oh,
222.
okay. So it's going to be 222. And what would be the sum of the atomic?
$86.
Okay, so 86. All right. So of all these options, the one that fits that would be this one right here. All right. So the answer would be this right here. Now, in some cases, well, not in some cases. Well, in some cases, you may not be able to, you may not be given the actual formula here, which is correct. In which case, if you didn't know what the formula for the element is, all you have to do is go to the periodic table and see which element has the same atomic number as 86, which matches up with it. And therefore, based on that, you can determine the element symbol. All right. Okay. Any questions about that? Any questions? Okay, so let's look at the next one. Let me clear this. Okay, so for the next one, what would be the mass number for whatever the particle is on this side?
$239.
Zero.
0.
Oh, 0.
Because you have 239 here, 239 here. So that means that whatever is here has no mass or no mass number. And then what about the the atomic number?
-1.
-1, right? Because 94 minus 1 gives you 93. So therefore the answer would have to be this one right here. All right. And basically that's what you do for the others. Do I need to go through the others? Yes, no? Is it necessary for me to go through the others? It's pretty much the same thing. Okay, I'll take that as a no. So what I'm going to do is scroll down. So I leave you to try those on your own. These are all basically the same thing, balancing equations, balancing nuclear equations. So let me scroll all the way down to okay, so let's look at this question here, which deals with carbon dating. And if you watch the videos, you know that carbon dating is useful. It's a technique that is used to determine the age of, you know, something that is once living, biological species or biological artifacts that was once living and died and, you know, for some time. And we can use this method to determine the age of that particular artifact. Now, there's an equation that you can use, which is based on the fact that the kinetics of decay of a radioactive material, it follows first order kinetics. And give me 1 minute here, let me just check something out here. Okay, so the equation, let me just bring this up here, that you're going to use to determine well, you're going to use different forms of the same equation. Let me just quickly describe what's happening here. So basically, whenever you have nucleus, which is undergoing radioactive decay, right? The rate of the reaction will be equal to, of course, the change in the number of nuclei divided by change in time, minus sign here because it's decreasing. That number is decreasing. And the rate can also be equal to lambda times n. Now, lambda times n, lambda is what we call the decay constant, and n is the number of nuclei, and that product is equal to the activity. And the activity can be measured using what is known as a Geiger counter, which I described in the videos. So if you want to be reminded of that, then you can go back and watch a video. I won't go into that right now. But basically, because the rate is equal to these two terms, you can set this equation up, and then we solve for n. And it turns out that n is equal to the initial number of nuclei multiplied by e to the minus lambda t. Now, remember I said that lambda is called the decay constant. It's similar to the rate constant for first order chemical reaction. And therefore, we can express this relationship this way. We can also express it this way. And we can also write an expression for the half-life, which is the same as the half-life for first order chemical reaction. The only difference is that instead of using a rate constant here, we use lambda. So half-life is equal to ln2 over lambda, all right? So that's basically how that the first order decay works out. And that's what you're going to use now to solve this particular problem. Now, this problem, going back to the problem here, it says a piece of wood from an ancient artifact has a carbon-14 activity of 11.7 disintegrations per minute per gram of carbon. And it says a current carbon-14 activity in fresh samples is 15.3 disintegrations per minute per gram of carbon. And it also tells you that the half-life is 5,730 years. So the question is asking, what is the age of the wood sample, all right? So the equation that comes immediately to mind, let me get my pen here, is ln n over n0 is equal to minus lambda t. That's one of the equations I just showed you. Now, because activity is equal to n times lambda, we can replace n and n0 here with a and a0, right? Where a is the activity of the fresh sample of the particular wood, and a here is the activity of the artifact in terms of the disintegration or the activity, all right? So the aim of this exercise is to find t. So therefore we can rearrange this here to get t is equal to minus 1 over lambda ln a over a0. Now we know what a is. A is equal to 11.7 disintegrations per minute per gram, and a0 is equal to 15.3 disintegration per minute per gram. So the only thing we need to find to get t, which is what we're trying to get, is lambda. Now lambda, as we said before, is the decay constant. All right. So basically, as we said before, the half-life is equal to ln2 divided by lambda. What we need to find is lambda, which would be equal to ln2 divided by ln2 divided by the half-life. And we know what the half-life is because they gave us right here. So 5730 years. You're going to divide ln2 by that number. And according to my calculations, and again, please check to make sure I'm doing this correct. But according to my calculation, this will be 1.21 times 10 to the minus 4 years to the minus 1. All right. So this is lambda, and we're going to put the lambda value where it is right here in this equation. So now we can find the time or how old the artifact is. That will be equal to 1 over 1.21 times 10 to the minus 4 years to the minus 1 multiplied by ln, and then A would be 11.7 disintegrations per minute per gram divided by the value for A0, which is 15.3 disintegrations per minute per gram. And that's basically the setup. And when I did that calculation, I got 2.22 times 10 to the 3 years. So in other words, same thing as 2,220 years. So that would be the age of the artifact based on the current carbon-14 activity. All right. Okay, any questions about that one? Any questions? Any questions?
How
Yes,
did
sir.
you, so A equals N lambda,
Yeah,
right, at the top. So how did you replace N with lambda? Or sorry, N with A in the first
because,
equation there?
okay, so since A is equal to N lambda, that means that A0 is equal to lambda N0, right? Remember, N represents the number of nuclei, right? A represents the activity, okay? So because of the direct proportional relationship between A and the number of nuclei, we can replace this here with this, because if I divide this by this, I'm going to get A over A0 is equal to N over N0, because the lambda will cancel out, right? So I can effectively replace this ratio between N and N0 with this ratio, which is what I have here.
Okay.
You see what I'm saying? Okay. All right. Any other questions before we move on from this one? Any other questions? Okay, so I'm going to take it. It's okay for me to clear this. All right. All right. So scrolling down. Okay, so the next question says, the half-life of a nucleus radon-222 is 3.88 days. How many milligrams of 5,000 of a 5,000 milligram sample of radon-222 remains after 60 days? Okay, what I'm going to do here is assume that, and I probably should have included that here. I'm going to assume that there's a decimal point here, which makes this 4 sig figs, all right? So the question is asking how many milligrams of the original 5,000 milligram sample of this particular nucleus will remain after 60 days, all right? The half-life is 3.88 days. So going back to this equation then, ln n over n0. Again, we can do, and this will be equal to minus lambda t. We can also equate this to ln m over m0, where m is the masses of the, m0 would be the original mass and m would be the mass after 60 days, right? And again, there's a proportional relationship between the number of nuclei and the mass of the radioactive substance, all right? So again, it's kind of similar to what we did before, excepting that this time now, we are trying to find m, all right? Now, we can rearrange or express this equation differently by writing it this way. M over m0 is equal to e to the minus lambda t. And therefore, we can say that m is equal to m0 e to the minus lambda multiplied by t. So what do we have? We have m0, which is the original mass. We have t, which is the number of days. And the only thing we don't have directly is lambda. But remember now, lambda is equal to ln2 over the half-life. And we're given a half-life here, which is 3.88 days. So ln2 divided by 3.88 days. And according to my calculation, that works out to be equal to 0.179 days to the -1. So that goes here. So we have everything now that we need to calculate M. The initial mass is 5,000 grams. Multiplied by E to the minus lambda, which we calculated to be equal to 0.179 days to the -1, multiplied by the number of days, which is 60. And when I did that calculation, I got, you know what, let me do this again. I think I may have made a mistake here. 0.179 times 60. Then I put a minus sign in front of that, and then I do shift. And then I multiply by 5. So 1,000. Okay, so according to my answer, I got 0.1083 grams. So this would be the final answer right there. All right. Okay, any questions about this one? Any questions? Okay, let me clear this.
Wait, should it be milligrams?
I'm sorry, you're absolutely right, milligrams. Thank you for pointing that out. Yeah, that should be milligrams. Okay, any other questions or comments about this? Okay, let me clear this. Oh, I'm sorry.
When you're doing the Landum equals ln2 over half-life, when you do the ln2, do you just literally type in ln2 into the calculator?
Yeah, typically what I do on my calculator is just I find the natural log of 2 and then do the rest. Like in this case here, natural log of 2 divided by 3.88. And it works. So when you do the natural log of 2, it works out to be 0.693 and some other digits. All right.
Thank you.
Okay. Okay. Any other questions before I move on? Any other questions? All right. Let me clear this here. And let me scroll down. Okay. So let's see if you can do this one based on what we have done before. It says, what is the original mass of a carbon-14 sample or mass of carbon-14 in a sample if 10.00 milligrams of it remains after 20,000 years? And it gives you the half-life of carbon, which is the same as before, which is 5,730 years. Let me just say this. I don't remember if I made this point in the video lectures, but what you'll find is that different radioactive nuclei will have a fixed value for its half-life, all right? And that doesn't change, right? Because, of course, as we learned before, you know, things like temperature, pressure, and all that does not affect the rate of nuclear reaction. So carbon's half-life, carbon-14's half-life is always going to be 5,730 years, for example, all right? Okay, so how would you tackle this problem based on what we have done before? What equation comes to mind?
The same one we've been working with?
Which is ln A over A0 is equal to minus lambda T. But this time you're given the masses, right? Or you're given the mass after some time passes, right? So we're going to use ln M over M0. All right? Okay, so what next? What is the question asking for? This 10 grams represents what?
M0.
You sure about that?
Well, no, sorry, that's what we're looking for. That is M.
Exactly, because the question is asking for the original mass. That would be M0. The M here would be the 10 grams, all right? So we're trying to find M0. So what I would do is, you know, something similar to what we did before. Find an expression, in this case, for M0. Now, based on this equation here, excuse me, I'm sorry. Based on this equation here, we can express this as m over m0 is equal to e to the minus lambda t, right? Which means that m0 will be equal to e to the will be equal to m times e to the lambda t, all right? So basically we need m, and we need lambda, and we need t. Now t is given as what, 20,000 years. M is the 10.00 grams. So lambda is what we need. So how do we find lambda?
ln2 over half-life.
Exactly. So in this case, it would be ln2 over the half-life, which is 5730 years, right? So that would be equal to 1.21, according to my calculations, 1.21 times 10 to the minus 4 years to the minus 1. Okay, so what next?
We plug in lambda into the above equation.
Okay, so m0 would be equal to m, which is 10.00 milligrams, times e to the minus the lambda that we calculated, 1.21 times 10 to the minus 4 years to the minus 1, times 20,000 years. And when I did that calculation, the answer I got was 112.5 milligrams, or is it grams? Milligrams. So it should be milligrams, all right? And that's basically how that is done. Okay, any questions about this? Any questions? Okay, so let me clear this and scroll down. Okay, now what we're going to look at here is a very important concept when it comes to nuclear reactions, and that it has to do with what we call the mass defect, all right? Now, the mass defect is basically somewhat of a measure of the stability of a nuclei, or a nucleus, I should say. And it's based on the concept, which kind of sounds counterintuitive, to be perfectly honest, but it's actually a scientific fact that if you take any sort of nucleus, right? For example, the hydrogen-3 nucleus, right? You would think that the sum of that nucleus would be equal to the sum of the individual particles that make up that nucleus, right? So for example, in the case of the tritium isotope, you'd expect that the tritium isotope, which is the hydrogen-3 isotope, so this would be the hydrogen-3 isotope. If you break it up into its individual particles, you're going to end up with 1 proton plus 2 neutrons. All right? So you would expect that the total mass of the particles that are on this side of this equation would be equal to the total mass of the hydrogen-3 nucleus. Turns out that that is not so, right? There will be a difference in the masses between the products and the reactants in this particular reaction. And that difference is called the mass defect. And it's a reflection of the amount of energy that has either been absorbed or released as you go from reactant to product in this case. Now, in the case of a nuclei splitting up into its different particles, that value will always be positive. Energy is always required for that. So therefore, the difference in the masses would be equal to, would be greater than 0, would be positive, all right? As you go from reactants to products. And there are certain things you can calculate based on the mass defect. So if delta M represents the mass defect, then the amount of energy that is needed to break up the nucleus into its constituent particles will be equal to delta M C squared, all right? So delta M would be the mass defect, and C would be the speed of light, which is 3.00 times 10 to the 8 meters per second, all right? And I should say that in this equation here, the units of mass defect must be in kilograms. Now, if the units is in kilograms here, and C is in meters per second, then the units of the binding energy, that's what we call this, the binding energy, would be in joules, all right? So that's basically how we relate the binding energy, which is the energy needed to break up the nucleus, into its constituent particles, all right? So that's what we'll be doing in this part of the question here. It is asking for the mass defect of this isotope, that's delta M, and that would be equal to the total mass of the different particles present. Now there's 1 proton and 2 neutrons, right? According to the information provided here, the mass of a proton is 1.007825 AMU. And then we add that to 2 times the mass of the neutron, which is given here, which is 1.008665 AMU, all right? So those are the products of this reaction, where we sum up the number of the masses of the particles produced when you break it up. And then for the intact nucleus here, they gave you that the mass of that nucleus is this right here. So that would be 3.0160490 AMU, all right? So once we calculate this, according to my calculations, this works out to be equal to 9.106 times 10 to the minus 3 AMU, right? So that would be the mass defect, all right? Now, that's the A part, okay? So before I move on to the B part, any questions about this? Any questions?
Professor, I'm sorry to interrupt. I was doing the calculating for number 23, and I just wanted to make sure I got the right answer because I didn't hear the answer while I was using the
okay, so number 20, all right, let me pull this up here. For number 23 said?
Yes, sir.
Okay, oh, so you want to know what the answer is for number 23?
Yeah, I want to make sure I got the right answer. I had the same answer.
According to what I have here, the answer, the final answer is 112.5 grams.
Okay.
That's what you got?
No.
Oh.
I got to figure out where I went wrong. So thank you.
All right, no problem.
Well,
Okay.
actually, I wanted to say that I also didn't get that answer.
Okay, let me do this again. 1.2 times 10 to the minus 4 times 2,000. I'm sorry, 20,000. And then I put shift. Oh, wait a minute. 1.2 times 10 to the 4 minus 4 times 20,000. And then I multiply that by 10. Okay, I got 110.2. Is that what you got?
Well, I heard you say you put an E to the 1.21.
Yeah, exactly.
I have negative 1.21. Is it
No,
supposed to be positive or negative?
It should be positive.
Oh,
because
okay, okay.
Because you're trying to find M0, not M. If you're trying to find M, then yes, there will be a negative in front of that, but you're trying to find M0, the original mass. So let me do this again one more time just to make sure. 1.21. Oh, I missed the 1. Okay. Times 10 to the minus 4 multiplied by 20,000. And then I do shift, and then that, and then I multiply by 10. Okay, so the answer I got is 112.5. So I'm pretty confident that you made a mistake somewhere. I don't know what it is. Maybe it's a minus sign or something. Maybe you included the minus sign where you should.
Yeah, I think that's what I did too, because there was
Yeah.
a negative on my paper and it gave me a totally different answer.
Yeah. Okay. All right. So let's go back to what we were discussing before. Scroll down. Okay, so this is what we were discussing before. Hold on, wait a minute. Right, this is where we're at, right? So the next question is, what is the binding energy of this isotope? So as I said before, the binding energy, let me get rid of this here. The relationship between the binding energy and the mass defect is given by this equation here. Is given by this equation here. Delta E is equal to MC squared. All right. Now, or I should say delta E is equal to delta M times C squared. Okay. The key thing about this, as I said before, is that the mass here must be expressed in kilograms and the speed of light must be expressed in meters per second, so that delta E will be expressed in joules, right? Now, if we do that in this case, what you'll find is that the mass we calculated earlier, the mass defect is 9.106 times 10 to the minus 3 AMU. And what we have to do is convert this to kilograms, right? Now, there's a relationship between the kilogram unit and the AMU unit, which is available in the tables. So let me go to the tables here. Where is it? Tables. And if I'm not mistaken, it's given where it says fundamental constants. That's where it is located.
That brings up a good question. When
Yes,
we
ma'am.
take our tests, are we going to have access to all of this stuff?
Yeah. You can just basically, well, you mean test number 2?
No, the at-home tests.
Oh, yeah. I mean, you can just go to Canvas and get the tables. In fact, you need to use the tables as given. I'm trying to, okay, so here's a relationship between the AMU unit and the kilogram unit, right? So we can put above in the conversion factor here. Up top, we're going to put 1.66 times 10 to the minus 27 kilograms. And below, we're going to put 1 AMU. All right. And we work that out. So let me do that right now. 9.106 times 10 to the minus 3 multiplied by 1.66 times 10 to the minus 27. And according to my calculations, this works out to be equal to 1.51 times 10 to the minus 29 kilograms, all right? Okay, so let me get out of this here and go back to okay, go back to this right here. Okay, so let me get my pen again. All right, so to calculate the binding energy now based on this, that will be equal to 1.51 times 10 to the minus 29 kilograms multiplied by C squared. Now C is equal to 3.00 times 10 to the 8 meters per second, all right? That would be the speed, but you have to square that. And then we work this out. And that works out to be 1.51 times 10 to the minus 29 times 3 times 10 to the 8 squared. And according to my answer, that would be equal to, round off to 366, that'll be 1.36 times 10 to the minus 12 joules, all right? So that's basically one way of determining the binding energy. Now, another way is using the information that's provided earlier, where it says here that 1 AMU, you'll notice it says here that 1 AMU is equal to 931 mega electron volts. Mega electron volts is, well, electron volts is basically a measure of energy as well. Let me explain what we mean by that. And for those of you who are going to do physics, you're going to meet this. What topic? I think you guys will be doing nuclear physics as well. So pretty much some of the same things you'll encounter. But anyway, 1 electron volt is equal to 1.60 times 10 to the minus 19 joules. All right. So basically, if you were to take 1.36 times 10 to the minus 12 joules and convert it to electron volts, this is what you would do. This will be joules. You're going to have 1 electron volt up top, 1.60 times 10 to the minus 19 joules below. And let's see what that gives. 1.36 raised to the times 10 to the minus 12 divided by 1.6 times 10 to the minus 19. And according to my calculation, this works out to be equal to 8.50 times 10 to the 6 electron volts, which works out to be equal to 8.50 mega electron volts. All right, it should be 5 here. Let me erase this so that it looks more. So this should be 5 here. All right. Now, that brings us to this relationship here, because I could have avoided all of this here and simply take the mass defect here and convert it to electron volts. In fact, I could have taken this mass defect right here and convert it to electron volts, and I'll get the same answer. If I take 9.106 times 10 to the 3, 10 to the minus 3 AMU and multiply it by 931 mega electron volts divided by 1 AMU, you'll get the same answer, which should be 8.50 mega electron volts. All right, so it all depends on, you know, the type of units that the question is asking for. And if the question is not specific in terms of units, you can pretty much basically determine the answer in any units, basically. All right. Okay.
Professor,
Yes,
I'm a
ma'am.
little confused. What is the final answer for the question we're working on?
The B part. What is the binding energy?
Yes.
That's this here and this here.
Oh,
And-
okay. So we weren't done at the 1.36 times 10 to the negative 12.
Well, that could be the answer as well, because the question didn't specify the units.
Okay.
So
Okay.
if you left the answer like this, that's fine. I was just explaining, you know, some other alternative units. So if you could be asked, for example, for the answer in mega electron volts. You see what I'm saying? So I'm just showing you how to do that.
Okay. Thank you.
All right. Okay. Any other questions before we move on? Any other questions? Okay. So let me clear this here. And in the remaining 5 minutes before our first break, let's answer the next question, which says, in the C part, what's the binding energy per nucleon, right? Now, a nucleon, just in case you missed it in the video lectures, is basically a particle that is present in the nucleus, right? So in the case of the hydrogen-3 nucleus, this would be the number of nucleons, right? Basically, it's the same thing as the mass number, right? So to find the binding energy per nucleon, we take the answer that we got from the B part, which is 8.50 mega electron volts, and divide it by the total number of nucleons, which would be 3. And whatever that gives, that would be the answer. So let me see here, 8.50 divided by 3. So according to my calculation, this gives 2.83 mega electron volts per nucleon. All right, and that's basically how that is done. And let me just say that this actual quantity, the binding energy per nucleon, is used as a measure of the stability of the nucleus, right? So basically, if you want to make comparisons between two different nuclei and you want to figure out which one is more stable, you basically calculate the binding energy per nucleon. The higher the binding energy per nucleon, the more stable the nucleus is. All right. Okay. Any questions about this? Any questions?
So in
Can you
order
also do it with
to,
the, oh,
yeah, I think we're going towards the same thing.
What's that?
Wait, are you, in order to do this, do we have to have it in mega electron volts?
No. Like I said before, it could be in joules. It all depends on, you know, how the question is worded. So you could have just as well used the other value. What was the other value? I don't have it here. What was the value in joules that we calculated in the B part?
1.36 times 10 to the negative 12.
Okay, so you could have done this, right? And whatever answer you get, that would be the answer. So it all depends on, again, you know, if the question is specific about the units. Was that the question that the other person was trying to ask?
yeah.
Oh, okay, right. So it depends, you know, on the question itself. If the question is not specific about the units, this will be just as correct as this. All right. Okay. And if you understand number 24 that we just did, then you should be able to do number 25. Let me clear this here. Let me get rid of that. Let me scroll down. So let's see if you can do number 25. It says, what is the mass defect of this nucleus? And they gave you the mass of the carbon-12 nucleus, 12.00000 AMU.
Are we still using the data that was above with the mass of the proton and the mass of the neutron?
Yes, ma'am. So delta M would be equal to what? Now, in the case of carbon-12, right? What would be the number of protons and neutrons present in that nucleus? Let's start off with that, because that's what you have to figure out first. How many protons are in carbon-12?
6.
Right, so there are 6 protons. And how many neutrons are in the same nucleus?
6.
Okay. All right, I'm going to take a break now. All right, so at least I got you started on that. So we'll restart at 11, all right? Okay, I am back, folks. All right, so we were looking at this question and we came to this conclusion here concerning the makeup of the carbon-12 nucleus. So the question now is, based on this, how would you calculate the mass defect of this nucleus? So let me hear how you'd approach this. Anybody? Well,
Would you do 6 times 1.007825
okay,
plus?
hold on. 6. Oh, shoot. Excuse me 1 minute here. This person is calling me right in the middle of class. Okay, I'm sorry about that. 1.00 what?
7825
7825 AMU. Okay.
plus
And then-
6 times 1.008665 AMU
8665 AMU. Okay.
minus 12 point. Do you have to add all the zeros?
Yep.
Okay, 12.
12.00000 AMU. Okay. And okay, so when I did that, I got 0.09894 AMU. All right, so that's how you would do the A part of this question. Okay, very good. This person keep calling. Okay, so that's basically how you do the A part. Now, as far as the B part is concerned, let me clear this here. And let me scroll down. It's asking for the binding energy. All right, so how would we calculate that based on what we got in the first part?
Isn't that the delta E equals delta MC squared? So you just plug
Ex-
in the value you just got for delta M.
Yes, but you have to be careful
Okay.
in terms of the units, because remember, you're right about the equation. Delta E is equal to delta MC squared, right? But delta M would have to be in kilograms and C would have to be in meters per second, right?
Correct.
So, and we have the answer. What was the answer again from the first part? 0.09894, right? We have to convert that to kilograms. And we looked at that before. What was the conversion factor?
1.66 times 10 to the negative 27.
Thank you. So we're gonna have, whoops. We're gonna have 1.66 times 10 to the minus 27, you said?
Yes, sir.
Okay, over 1 AMU, right? So that takes care of the delta M, and then we multiply this by 3.00 times 10 to the 8 meters per second, and we have to square that. And that's basically how we get the binding energy. So let me see here. 3 times 10 to the 8 squared, multiplied by 1.66 times 10 to the minus 27 times 0.09894. And the answer I got is 1.45 times 10 to the minus 11. And the answer would be in joules. So that's basically how that is done. And if you want to, you can convert that to mega electron volts, I won't do that right now. Okay, then we need to find the binding energy per nucleon. So how would you do that part?
You're gonna divide that value by the number of nucleons, and I'm not sure, is that given somewhere in the problem? I don't have the paper.
Well,
on
the
me.
number of nucleons, remember, by definition, the number of nucleons would be the number of, I'm sorry. The number of nucleons would be the number of particles, and that would be given by the mass number. Okay, I guess I erased what I had before. Sorry about that. So this
Would
is
that
the
be
mass number.
12?
Exactly. So whatever the answer I had, which I erased accidentally, what was the answer that I got from the B part?
1.45 times 10 to the negative 11 joules.
1.45 times 10 to the 11 joules, you said?
Yes,
Minus 11.
minus 11.
Okay. Minus 11 joules. We divide that by 12 nucleons. So let me see here. Was it 1.5, 1.47 you said?
It's 1.45.
Oh, okay. I'll go with that. 1.45 times 10 to the minus 11 divided by 12. And the answer I got here is 1.20 times 10 to the minus 12 joules per nucleon. And again, you could convert that if you're required to into mega electron volts by dividing by 1.60 times 10 to the minus 19. Okay, so that's basically the same thing like we did in the previous question. And if you understood those two, then you should be able to do question number 26. Pretty much the same thing. Numbers are different, of course. And that's basically the end of this assignment. All right. Okay, so let me see here. So that's basically it for this course. So as I said before, I'll be posting the test number 3 and the final exam online. Both of them I'll have posted by this evening. And what did I say the deadline for the test number 3 is? If I remember correctly, I said by Friday, right?
Yes.
Right, the 4th. Let me write this down before I forget. So August 4th would be test number 3. Deadline. Okay, and I think I already posted in Canvas what the deadline is for the final exam, which should be on the 7th. Okay, so that's basically it, unless you have any questions you want to ask about anything, any topic, any area of difficulty, any problems?
So going back to what we were just working on, when you were separating it into protons and neutrons,
Okay.
can you go over how you do that?
Okay, it's simple. Remember what the mass number represents. Let me clear this here. Remember, the mass number represents the total sum of protons and neutrons, right? So for example, in the case of carbon-12, right? This would be the isotopic symbol, right? So 6 would represent the number of protons. So I'm going to put 1p here, 6 here, right? And 12 minus 6 gives you the number of neutrons. So that would be 6 times 1. Whoops. 6 times 1, 0, n, right? And that's it. And if you look at this carefully, you'll see that it balances out because 6 plus 6 gives you 12. And 6 times 1 gives you 6 plus 0 gives you 6.
Okay, so like in the case of number 26, it says iron 56. So 56
Okay.
would be the mass number.
Right. So iron 56. What's the atomic number? You'd have to look that up in the periodic table. I think it's 26, if I remember. Let me see here.
Yes, 26.
Okay, so iron is 26, the atomic number, right? So basically that would be 26 protons. And then 56 minus 26 gives you 30 neutrons.
And what does the 1/1 stand for?
Okay, so this one here would be the mass number, just like in any other symbol. And this here would be the atomic number.
And that's what you went over last class, right? And I'm sure it's in the
Yeah, yeah. Mhm.
I briefly remember that a little
Right.
bit from the last class.
Right, the top number in all these symbols. It doesn't matter if it's this, or even the protons and neutrons, or the beta particles, or the positron. This is the positron here. The top number is always the mass number, and the bottom number is always the atomic number.
So for protons, it's always going to be 1/1.
Exactly.
Okay.
One will be the mass number, one will be the atomic number. For neutrons, it's 1 being the mass number and 0. So effectively, for the purposes of balancing these equations, the mass number for neutrons will be 0. And then in the case of beta particle, which is what this is, the atomic number is -1, the mass number is 0. In the case of positrons, the mass number is 1, the atomic number is 0. In the case of alpha particles, the mass number is 4 and the atomic number is 2. So the top number is always the mass number, the bottom number is always the atomic number.
Okay.
Mhm.
As of
Oh.
right now, is there any situation where we have to worry about the masses of or those configurations for positrons and beta particles?
What do you mean?
Like, is that going to show up on a test?
It could show up when it comes to balancing equations. Like the ones that we saw earlier. If I were to, I'm quite sure if I scroll up here, let me see, hold on. Oh, shoot. If I scroll up here, there are some equations where, let me get rid of this here. Let me clear this and then do this. Okay, I'm quite sure in all of these equations that I have up here, there are some instances where, let me see if I can find one or two instances where, okay, like in this case here, you have a positron right here, right? So you have to take that into account when you're trying to identify the missing particle right here. I think that to answer your question, I think, you know, those particles will only, at this level at least, will only appear when you only have to be concerned with when you're balancing equations.
Okay.
I'm trying to find another example. Well, here's an alpha particle here. So yeah, that would be, you know, that would be, let me see it. Here's a beta particle, right? So basically, you have to be concerned with those when you're balancing equations.
But when you're looking at like that example there, you would still want to make sure that the mass number and the atomic number add up to
Exactly.
whatever
On
the
both,
reactants are on both sides. Yeah.
should be the same on both sides. So like in this case, let me just look at this one here. In this case here, the mass number has to be conserved. So that means whatever the particle here, the mass number is going to be 42. And then you have 19 here, you have -1 here. That means that this has to be 20. Because 20 minus 1 gives you 19. So therefore, the answer would be that one. All right. So that's basically how you answer these questions. Total mass numbers should be the same on both sides, and the same would be true for the total atomic numbers. Okay, any other questions, problems, issues? Well, let me ask you this. Do you think we should meet on Wednesday? I mean, for review purposes?
Yes.
Oh, okay, all right. So we're going to meet on Wednesday then. And you can come with your questions. Now, of course, I cannot answer any questions directly from your take-home assignments, test, and final exam. I know I have to say that after many years of experience, I know that is something that I have to make clear. Okay.
And then are you going to post a final key, or are we just going
Good
off of all
question.
the
Let me
other
see if
keys?
Let me see if I can find one. That's a good question. Hold on. It looks like I already posted one, actually. Let me check it out here.
Yeah, I was out of
Uh,
town all weekend, so I wasn't able to check to see what you've put up there.
Okay, I published one already. So yes, you can check that out. I'm just scanning through it right now just to see what's in it.
And I know you said you can't answer any questions based off of the test you're giving us, but would you be
Mhm.
able to answer a question on the keys if we're
Oh,
confused
yeah.
on how you got to a certain, okay.
Oh, yeah. Mhm. Any questions accepting anything directly involving those take-home assignments? Or if I do, or let's put it this way, if there's something that you think you need clarification on in those assignments, then yes, I'd have to judge and see whether or not I'll be giving too much information, but like to directly answer questions from those assignments, you're on your own. Okay, any other questions, problems, issues? Any area of difficulty? Any further explanation needed?
I will definitely have to go over my notes and see if there's anything that I need to go back over. So I'll bring the questions that I have on Wednesday.
Okay, no problem, no problem, no problem. No problem. That's why they pay me the big bucks. Okay, so if there are no other questions, that's pretty much it for today. What I'll do is, since we ended early today, I'll hang out in Skype land, just in case you might have any questions between now and 1:10. And again, we're going to meet on Wednesday. And basically, I'm just going to set up the Zoom, and if you have any questions you want to ask during that time, that's basically what we'll be doing on Wednesday. All right. Okay. All right. So I'm going to sign off now. I'll be hanging out in Zoom. I mean, not Zoom, in Skype for the rest of the class time. So feel free to jump in and give me a call. And if you have any questions you want to ask, please feel free to do so. All right. So,
I have a
yes.
question. When is assignment 8 going to be due? Is it due?
Oh, good question. Assignment 8. Thank you. And I totally did not even think about that. Let me see. Today is what? Today is the 31st, right? So I would say I'll make it due on Wednesday. So let me just set that up right now. So assignment 8. Let me see. So that would be Wednesday would be the 2nd, right? Let me see. So let me make sure that it's all set up correctly. Okay, so let me just check one more thing. Okay, so now the Dropbox should be available. So I've set the deadline date for that to be Wednesday, August 2nd. All right. So make sure, as I said before, make sure it is done in ink, make sure that your name is on every page, and make sure also that it's submitted as a PDF document. All right. Okay. Any other questions before I leave or before we sign off?
You said you were posting the finals today later as well, right? You're
Yes,
posting
the
both of them?
final and test number 3 later on
Okay.
this evening. Yeah.
Thank you.
All right. Okay, so there are no other questions. I'll see you guys on Wednesday if I don't hear from you later on today. All right. All right. Take care. And I'll see you then.
Thank you.